To start today's assignment, you need to get a paper and count the dots. And you're not allowed to make any marks on your paper at all when you count the dots. And the whole point of this is you're going to make mistakes. And that happens all the time in statistics. So there are a whole bunch of dots here. Count them without making any marks. And then you will put your first count right here. And then you recount. And you put your second count here. And then come up and put your numbers on the board. And then we'll enter them into our calculator. So I'll pause the video. And then you can make your counts and then come up and write them on the board. Okay, now that you're done with that, where did it go? There we go. Here are the numbers. I entered them into the computer and I sorted them. And this is what we get. So there are 42 numbers here. They're sorted. And we need to draw a histogram. So our range is from 95 to 112. So what is that? 12 and 5 is 17. And how many boxes do we have on our paper? 3, 4, 5, 6, 7, 8, 9. So I'm going to go by twos. And then we'll just have one that's not, that doesn't actually fit. So how am I going to do this? I'm going to print those. No, I have them in my calculator. That's what I'm going to do. Okay. So here is my histogram and my box. And I'm actually going to add one box to it. And yours might look a little bit different, and that's okay. So I will say 95 and 96, 97 through 98, 99 and 100, and then 101 to 103, well, 102, and then 103 to 104, 5 to 6, 7 to 8, 9 to 10, and then, oh, I didn't even need an extra box, 11 and 12. Is that how you guys divided them up? Then I need to put the count in each box. So I have 1 in that range, 3, 1, 2, 3, 4, 5, 5, 1, 2, 3, 4, 5, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 14 there. And then 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7. So what you guys got? And then 7 to 8. 1, 2, just 2. 9 is 1. And then for some reason we have 3 12s. Okay. So my markers aren't really big enough to write the numbers down there, but I need to go as high as 14. And actually, the width of each one of these is 2, so I should really only go up to 7 to get the areas right. But as long as your intervals are the same width, it doesn't really matter. So whether that's a 7 or a 14, I'm not going to be very picky. So that would be 7. 1, 2, 3, 4, 5, 6, 7. Okay. So now I graph up to 1, and then up to 3, and then 1, 2, 3, 4, 5 would be there, and then 5 again, and then 14's all the way at the top, and 7 would be right there, and then 2, and 1 and 3. And this middle one is from 103 to 104. So that's actually not there anymore. So, oh, that's not what I meant to do. So what do you think the actual count is? If you had to guess, if you had to bet, what would you guess? Somewhere in the 103 or 104 range. Which one would you pick? We have 1, 2, 3, 4, 5, 6 that are in the 103 range. And then 1, 2, 3, 4, 5, 6, 7, 8. 8 that are in the 104 range. So we would probably guess 104. Right? Are we sure that it's 104? Not yet. We don't know. Okay? Is there any way to truly know? I guess we could be a little more careful, right? Why was there so much variation here? What happened? Well, people make mistakes. You know, maybe you're not very good at counting. Maybe you skipped some dots. Maybe you counted some dots more than once. There are a whole bunch of reasons why this is not accurate. And one of the purposes of this assignment is to show you, even when the true information is sitting right in front of you, you might not collect the data correctly. Okay? The population is there on the paper, but transferring the population into a data set, there are problems. Okay? So on the second page, it asks, does the histogram follow the normal curve? Would you say this is a normal curve? I would say, yeah, it does. Big in the middle, lower on the edges, and you might get a little bit worried about, well, this isn't what it's supposed to be, but as long as it generally follows this shape, we're fine with it. So yes, this does follow the normal curve, which is nice, because then we can do chapter 5, which is what we're going to be doing in this class over and over and over. So the next question, how many class counts are there? There are 42 in this class. Okay. And then what is the average of the class counts and the standard deviation? How do I find that? Go to stat, calc, one variable stat, and I get my average is 103.6, and my SD is 3.9. Okay. How many of the class counts would we expect to be within one standard deviation of the average? 68% of 42. So 0.68 times 42 is 28.5, 28.56, but we have to round it. Which way are we going to round? We'll round it up to 29. Okay, so we expect 29 of the counts to be within, let me recalculate this. So 103.6 plus or minus 3.9. So 103.6 plus 3.9 is 107.5, and 103.6 minus 3.9 is 99.7. So let's count them. How many numbers are there between 99.7, so we're going to count the 100s all the way up to the 107s. So look on your calculator, and can you see how nice it is that it's sorted on your calculator? Makes your job a lot easier. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 32. 31. Is that what you guys got? 31. How did we do? We expected 29, and we ended up having 31. Why is that 31 not exactly 29? Well, it's because our graph does not exactly follow the normal curve, but it's close. And in statistics, close is as good as you're ever going to get. If you ever have data that is perfect, it is not really data. It's not true data. It's been doctored or filtered because exact data does not really exist. Why does it not exist? Well, for one thing, you can't talk to everybody. That's a problem. But for another thing, even when you can talk to everybody, there are still mistakes that happen, right? You write something down wrong. You count 2 dots twice. You skip a dot. That is always going to happen, and that is called chance error. And this chapter is all about chance error. What happens when we try to collect data and write it down? It will never, ever be perfect. Okay, so the next question. How many of the class counts would you expect to be larger than 2 standard deviations from the average? How would you figure that out? How do I create an expected class counts that are larger than 2 standard deviations from the average? How should we do that? Using the normal curve. Well, this is my average, and I want to go out here to plus 2. So what do I do? How do I find this area? We could use the 100 trick. How did you find 2.5%? Good. So if we go plus 2 and minus 2, this is 95%. And actually, if you look at your yellow sheet or the one up on the wall, if we go out to plus 2, we actually get 95.4. So 95.4%. And now, Megan, what do we do? Subtract that from 100. So 100 minus 95.4 is 4.6%. And what do I do with that? Divide that by 2, and I get 2.3%. Okay? Is there another way to calculate that? How would you use your calculator to find that percentage? So you would do from 2 to 5 on your shade norm, and you'll get 2.3%. Okay? Now, if there are 42 measurements in the class, how many of those should land over here? Well, 42 times 0.023 is 1, right? 0.966. So if I take 103.6, which is my average, and I add to that 2 copies of the standard deviation 3.9, 103.6 plus 2 times 3.9, I get 111.4. How many of my scores are bigger than 111.4? 3 of them, and they're all 112s. Okay, so I expected 1, and I ended up with 3, which is pretty close. I'm not too far off. All right, what would happen to this chart, to my histogram, if I were to have 100 people count the dots? What do you think is going to happen to my histogram? Are we still going to have variation? Yes. But what will happen to the blue histogram as more and more people do this? It's going to become more and more like the normal curve. Okay? The more people that do this, the more it's going to look like the normal curve. So, having more people having a larger data set actually helps. Our data set is pretty small, 42, and you can see it doesn't follow the normal curve very well. And maybe you guys are just particularly bad at counting. I don't know. But if you have more and more people do this, then your histogram will look more and more like the normal curve. And the assumption is, if an infinite number of people do this, then the normal curve and the histogram will look identical. That's the point. So in statistics, the larger your data set, the more accurate your histogram is going to be, the closer it's going to look like the normal curve. Okay, second to last question. Are there any values that are so far from the average that you don't think they should be counted? Well, we had one that was right here. We had 195. What is the z-score for that? Well, 95 minus 103.6 is going to be 8.6, negative 8.6. Divide that by 3.9. And I get negative 2.2. What does that mean? Negative 2.2, or 2.2 SDs less than average. Okay? So at some point, we're going to have these things that are so far away. Wait a minute. This is just a huge mistake. Right? Something is going on here. And this is called an outlier. And sometimes we decide throw the outlier out, and sometimes we decide leave the outlier in. Now, in this class today, we didn't have, that's not really that far. Yeah, 112 is just about the same. It's 2.1 is what you calculated. So that's good news. Nobody was terribly off. Nobody was 3 or 4 or 5 SDs away. So we're going to go ahead and leave it. Okay. Now, I know you're all itching to do this. Go back to the first page. Scratch off the dots and see how many you get. And see if anyone still makes a mistake. And then when you're done, let's hand this in.